Okay, here we go. All right. Did I leave off with exothermic, endothermic, and then one with a bunch of bumps?
Yeah.
Okay. So which one was first here?
Exothermic.
The exo or endo?
Yes, exo.
So like that. Okay. And then we had that. And then we had, I don't remember exactly how it looked. Yeah, but which peak was the biggest? Three peaks.
The fourth one was big.
There's four. What?
Well, no, number 4. No, like the valleys.
No.
No, they were not.
The second and third bumps were the tallest, and they were the same height.
Well, I wanted one higher than the others.
Well, that didn't occur.
Make it number 4.
Make it 6.
Hold on. The third bump, I think, was supposed to be the highest. So make the third bump higher, Earl. There you go. Good job. All right. Okay, so we got potential energy here. We got time. Potential energy here. We got time. Potential energy here. We got time. Now, why are we talking about this? Well, there used to be a whole bunch of stuff I taught with activation energy. There's an Arrhenius equation that we used to learn about and needed to use, but now says the AP Bible you don't have to, so we're not going to. But you still have to have a concept of how to read this and how it affects rate. So this one is exothermic. Why? What would I write here? What word? What's the end of a reaction? What do you get at the end? What are those things called? Products, right? So products go here, and then I'm just going to put an R, reactants are there. Same thing here, reactants here, products here, reactants here, products here. We'll talk about the last one in a little bit. So this is exothermic because the energy of the products is lower than the energy of reactants. So at some point through this reaction, the reactants lost energy to the surroundings, and that would give us a negative delta H. This is endothermic because at some point in the reaction, the reactants gained energy and ended up with more energy as products. Can anyone label the delta H on these here? The heat of reaction is what delta H stands for. The energy change during the reaction. Anyone come up here and label the delta H? Great, what do you think? Do you want to come up and do it, or do you want to just tell me?
Come up and do it. Go do it.
Yeah.
Follow your heart. Go. Follow your heart.
The distance between the reactants and the products.
So between here and here?
Yes.
Yes, very good.
It's about 300 kilograms.
So there's your delta H right there. Here's your delta H, okay? Same thing here, from reactants to products. Here's your delta H. So this is positive because it's gaining energy. This is negative because it's losing energy. Very good. If I wanted to label the activated complex, also known as the transition state. Marcy?
Isn't that the top of the
Very top, right here. Very top is called the activation or activated complex or transition state. So if you don't know that, write that down. Transition state meaning you're transitioning from reactants to products. And then activated complex is just another term for that. Right at the top of the peak is where particles collide. And if it's an effective collision or a fruitful collision, as that one video that I showed you guys in the past, it will continue on and make products. If it's not effective, it'll stay as reactants. It'll go back to being a reactant that isn't reacting. What two things do you need for effective collisions? Proper orientation and sufficient energy. Right, they have to hit each other hard enough in the proper orientation. Okay, so that happens or doesn't happen right there. Okay, that's where they collide. Particles collide. All right. Who could label the activation energy? Where would that arrow go? The activation energy. Bree, go ahead. You want to come up this time?
No.
Yes.
From the reactants to the
Yeah, so from the reactants to the top of the peak here, okay, that's your activation energy. Very good. That's your activation energy. Now, AP Chem, they abbreviate that big E, little a. Big E, little a, that stands for activation energy. Now, let me look at my...
They do that.
Activation
Yeah,
energy.
Yeah, I love future wars.
So it's capital E, then sub A there, okay? So that's kind of it as far as what you need to remember. Now, let's just say, this number here is 100. Let's say this is in joules, and let's say this number is 100, okay? Joules, so go ahead and label those. Let's say the top of this peak is 200, but the top of this peak is 400. So let's say both reactants start at 100 joules. The top of the first peak here, that would be 200 joules. The top of this peak would be 400. Don't answer it too quick here. Think about it. Raise your hands. Which reaction would proceed faster? Which one would have a greater rate? So number 1, number 2. So the X over the endo. Start at 100, this one goes up to 200, this one goes up to 400. Which reaction would proceed with a faster rate or a larger rate, a greater rate? That means it's faster. Because remember, rate is molarity per second. So if you have a greater rate or a larger rate, that means there's more moles reacting per second, right? So if you have a rate of 2 molarity per second versus 200 molarity per second, obviously the 200 is reacting way faster. Same amount of time, more moles are reacting. So which one would react faster, have a greater rate? Raise your hands. Number 1, number 2. Number 1, number 2. Who's going to react faster? It has nothing to do with the fact that it's endo or exo. That delta H has nothing to do with that. I don't see any hands being raised.
Faster, do you mean react sooner? Or
You should give us magnets, and every
Same
time
thing.
you ask a
That's the
question,
same thing.
Throw it at whichever one you want. So it's kind of like darts.
Which one has a larger or a greater rate, an increased rate of reaction, meaning it reacts faster? It's the same thing. Those phrases mean the same thing. Dylan, what do you think?
First one.
Why?
It took less energy to start.
What's activation energy mean?
The amount of energy needs to react.
Yes, the amount of energy it needs to react. What is the activation energy of the first one? How many joules?
100.
100 joules. So this one, you need 100 joules to start the reaction. How many do you need here, Dylan? 300 joules. Which one do you think is easier to obtain, 100 or 300?
100.
Yeah, very good. Number 1 would have a faster reaction rate, an increased reaction rate. Number 1 would react faster because you only have 100 joules to go from reactants to the top of the peak. That's where the collisions occur. Here, it takes more energy, so therefore it would take longer to react. Does that make sense? You can't react until you get to the top. That's the activation energy. So if the distance here is shorter than the distance here, even though they look the same the way I drew it, that's irrelevant. It's the scale, right? You got to look at the scale. So that makes sense, hopefully? Everybody with me here? Okay. Now, let's label the products. Let's say this product here is, I don't know, we'll say 350. And then these products here, we'll say 50. Just kind of covering all bases here, make sure you understand this stuff. Which reaction, number 1, number 2, does the reverse reaction occur with an increased rate or a faster rate? A greater rate, a larger rate. All those things mean it reacts faster. So which reaction here, number 1, number 2, number 1, number 2, with the reverse reaction, meaning you start at the products and go backwards? Which reverse reaction would react or occur faster? Earl. Not even close, right? This one only needs 50 joules to get to the top. So if you're here, you're going to be up there very quickly. Here, we got to go 150. So in general, this always works out this way, that this reaction here, if it's endo, your reverse will always be faster than your forward. Why? You're already up there, right? And then for exo, it's the opposite. Usually the exo is faster. I mean, the forward's faster than the reverse because you're down here now, so you got a little bit further to go. So we're going to talk about reversible, which is equilibrium reactions, right after kinetics. Maybe we can get to that Friday, but for sure next week. So starting to understand that these reactions can go both ways is good to just get your brain ready there. That's about it, okay? That's kind of just Regents review a little bit, but maybe a little bit more complex, and there's a new symbol for you. You might see that, so I'm telling you because you might see that. They might use that symbol for activation energy. All right, now this guy over here, what's going on here? So did I number these two? Or did I number just? So 1, 2, 3, 4, 5, 6, 7. Okay, 1 and 7. Reactants and products. Oh, I'm sorry, I just remembered. What's one thing I forgot? What did we always label in Regents Chem on these things? The dotted line, what does that represent? If we add catalyst, that would look like this. It would be the same curve, just lower. So remember, that would be a catalyst, okay? So these energy profiles are, every reaction has these if you know, they're determined experimentally, and the rate of the reaction, which is what kinetics is, you know, can affect this. All right, so obviously the catalyst lowers the peak, so it reacts faster because there's a lower activation energy. That's what that does. It lowers the activation energy. It provides an alternate pathway for the reaction. Doesn't mean the collisions or the orientation or the collisions occur more frequent. It's not more frequent. It's just there's less. Well, I guess you can say it's more frequent because more reacting particles get to the top of the catalyst because they don't need as much energy. If you leave it at the original energy, some may not ever get there. But if you lower that, then those who would normally not react, then they would react. This actually reminds me, there's another curve I want to show you, so I'll have to find that. Just kind of review, we talked about it earlier in the year. But anyways, that's it for those. Back to this one here. We're going to learn more about this today with the reaction mechanisms. But what do you think's going on? How is this different than those? How many different activation energies are there? 3. There's an activation energy here from 1 to 2, from 3 to 4, and 5 to 6. So 3 different steps to this reaction. So when this is where we're headed with reaction mechanisms, this would have 3 steps. A 3-step reaction, okay? 3-step reaction. There are intermediates formed, okay? Intermediates are temporary. They're not sustained. Does anyone want to take a guess where an intermediate would form? And what an intermediate is where you have reacting particles, okay? They react, they form something that's fairly stable, but then that breaks apart and it forms something new. That breaks apart and then forms your final products. So anyone want to take a guess where these intermediates would be? We're going to learn about, I'm going to leave this over here, and then we're going to take some notes on these mechanisms. But I do want to show you that on the graph too. Yeah.
Would it be at 3 and 5?
She thinks 3 and 5 would be the reaction intermediates. What do you guys think? So again, an intermediate is temporarily formed, so reacting particles collide. They form something that's temporarily stable, then it breaks apart. So when I say stable, what should you think? Low energy. So does that make sense? Maybe. We'll find out. Okay. Oh, we need iPads too. Hopefully we're going to have to stop a little bit early. We'll see. It's annoying that we're not here. It's not their fault. Lights, please. I want to show you this graph again quickly. Thank you.
I like to sing.
It was on the cable.
What
wasn't it?
song?
And also on my
I
Spotify.
still don't know words of that one.
What the heck are you guys talking about?
We're getting this song of he's like, my name is Earl. Hi Earl. And then Earl's like, I like to sing. And everybody's like, what song?
That's how far I've gotten.
All right. Okay, so you might remember this. Hopefully you do.
Mrs. Q thinks you're super.
Okay.
I like to sing.
All right. Remember seeing this?
No.
No.
Wait.
Yes, we did it with like
Maybe.
the gases.
Mhm.
Oh, yeah.
Yeah. Why is the higher temperature starting to flatten out? Hold on. Think first. Don't answer. This applies to rate. These curves, this is the Maxwell-Boltzmann curve, it's called.
Higher rate.
There's actually another way you might see this graph.
Use one of these little markers.
Okay, why is the 300, why is it such a peak? 600 starts to flatten, 1,000. If we were to extrapolate this to 2003, whatever, it would get flatter and flatter. Why would it start to get flatter and flatter the higher the temperature? I don't like the units on this. That makes it confusing. But I should probably find another graph.
The same units as the rest.
What is it?
Like the same. Like,
No, it's different. Why are they different heights and why are they starting to flatten out here? Let's see if I can find another one. Better units. I don't like the units. Any thoughts? Ah, yes. Okay. This one is it's smaller, but I don't really want to zoom in because it screws up my whole thing here. This is molecular speed. This is number of particles. Number of particles on the Y, molecular speed on the X. Why would 100K be such a sharp peak? 1,000 starts to flatten out. These are about reactions, reacting particles at different temperatures. Any thoughts? Marcy?
Temperatures measure average kinetic energy.
Good. You're right. So why would 100K have more particles, a ton of particles right here at the top, and then it drops off so much? Whereas if the reaction takes place at 1,000K, the number of particles here at the peak is much lower, but then it starts to flatten out. It doesn't drop off so much. So let me restate that. At 100K, you have a lot of particles moving at this one speed. Okay, that's 250, let's say. But at 1,000K, you have less particles, right? This is why, less particles. But they're moving, all of the particles are moving at faster speeds because it's starting to flatten out. It isn't a point. Why does that make sense?
are the particles colliding up there and then the number of them decreases? They react.
Oh.
They react, okay, good, they're colliding, you're getting there. What do they do when they collide? Transfer energy. That's the answer. So these particles all become almost moving at the same speed because they are colliding and transferring, so there isn't a whole bunch of particles at one speed, because when they're moving slower, they're not hitting each other as often. When they're moving very quickly at 1,000K, they're moving very fast, they collide, and they distribute. Where's Ben when you need him? Wasn't it distributed or was it
Yeah,
dispersed?
it was distributed.
They're distributing their, this is appropriate, distributing their energy among more of the particles. So it's more of an average than here. That's just kind of all the particles at one speed because they're not colliding very often. So the hotter it is, the more collisions, the more spread out that energy is. That's why the curve starts to flatten out. That's actually, I think, really important for you to understand because that's why the reactions will proceed faster because there's more collisions. There can be more fruitful or effective collisions, and that's why you'll get more product, which is what you were getting at a little bit. Here's another way to look at it. This shaded area here, that's the activation energy, okay? That's the activation energy. And if T2 is a greater temperature than T1, okay, T2 will have more particles past the activation energy because they're hotter, they're more or have more energy, they collide more often. So there's going to be a larger percent of the reacting particles that are above that activation energy, so they are making products as long as the temperature is higher and it starts to flatten out. So you can relate it back to the other one. So if it starts flattening out, okay, let's say the activation energy is right here. Okay, let's say this is the activation energy. All of these red ones here are going to be making products. None of those green ones or whatever, blue, whatever you want to call that, none of the 100 are going to be making any products because the activation energy is here. They need higher temperature to reach that activation energy, and then more particles will be reacting and forming products. So the reason I'm going through this again, we talked about this with gases, is now it's more appropriate with this reaction rate stuff. So what do you need to know? That if you increase temp, reaction rates increase, more products are formed. I think you guys know that because there's more effective collisions. But can you relate it to this graph? So the flatter it becomes, the hotter it is, the flatter it becomes, the more particles will be to the right of that activation, meaning they've reached that energy to react. So that's how you can relate kind of something we learned early in the year to the rate of reaction kinetics. So it's important to understand. Let me say that again. Higher the temperature, the more particles will be past that activation barrier, and they can form products, and that usually means a flatter line. So I think that's important to understand. Again, there's a lot of concept questions on the AP test. That would be one. Okay, that would be one. It isn't always just calculations. There's a lot of those, but not always. I was looking at the midterm here. It's a practice exam, and some of the questions are tricky because they're concept. There isn't a calculation, so you got to think about it. Not necessarily this, but just in general. All right, so I wanted to make sure we went through that again. All right, we're going to do reaction mechanisms for a little bit, and then we're going to do all right, lights please. All right, so reaction mechanisms. Here we go. Reaction mechanisms. And again, these are determined experimentally, just like rate, just like the order. You can't get that data in the data table to figure out, the exponents. It's all experimental. You're not just going to be figuring this out on your own. All right, let's see here. Moving on. All right. So I'll give you some definitions here. I don't do this too often, but it might make a little more sense. So a reaction mechanism is a sequence of elementary steps. For those of you who say elementary, steps that leads to product formation. Okay, so elementary steps / elementary. Do we all say elementary in here? Bree doesn't? Bree says elementary? All right. I think I actually like that better, but I say elementary.
Say aluminium.
Your mom does.
Aluminium.
There's nothing wrong with that. Maybe there's something wrong with the way we say it.
We have to embrace our differences.
That's right, Earl.
Hey, Earl. Be you, because everybody else is taking
A series of simple reactions that represent progress of the overall reaction at the molecular level. Okay, so basically this curve over here is an example of a reaction where it shows all the elementary steps. Most reactions, this is hard for you to understand. It was hard for me to even understand when I first learned how to teach this stuff. That most reactions don't just happen in one step. So you don't take two reactants, they collide and make a product. Usually there's an intermediate. Oh, wait, we were supposed to give that away. But there's intermediates that form, and that's temporary. And then they react, and then they form another intermediate. And then they react, and then your final product. So things happen in steps, not usually in one big step. Okay, they happen in elementary steps, not just one big step. All right, so let's get an example here. So again, this is all proven experimentally. There's no way you're going to really just do this in your head. Here we go. All right, so if we take NO2 gas plus CO gas, NO2 gas, make sure you have a decent amount of space underneath this. At least maybe like a quarter of a page, half a page, depending on how big. Just to make sure, so because if you have to flip, when you're looking, you go back and look at it, it's going to be confusing. It's better to see it all in one. NO2 gas plus CO2 gas yields NO gas plus CO2 gas. Wait, what?
What?
This is CO. Sorry. My fault. I was like, that doesn't make sense. That's CO gas. All right. So NO and CO2 are not formed as a direct collision. Instead, an intermediate is formed first, then the products are formed. So this reaction actually does not apply to this. This is just something I kind of made up to help teach it, but this one has 2 steps, not 3, 2 steps. So in an intermediate, appears in the mechanism of the reaction, but not in the overall balanced equation. So there's an intermediate that is not present yet. It's not, I didn't write it on the board. So it's not in, that's the overall reaction. There is an intermediate that is formed. So the way a lot of books teach it, or teachers, how I teach it, we say it's formed early, consumed later. Formed early and consumed later. Just like breakfast. Yes. That is.
I consume it more.
Yeah, I kind of form it early and consume it early as well. But
Your mom gets up early.
I get it. I get it. No, it's decent. It's decent. All right. So
It wasn't even bad.
here's a pretty simple AP concept. I give you the elementary steps, which is the 2 steps that occurs before the overall reaction is formed, and then it would say which of the following is an intermediate. So you would do multiple choice questions. So based on what I told you here, let's see if you can pick it out. Okay, so you got NO2 gas, so this would be given to you, plus NO2 gas yields, this is our elementary steps, elementary. When we get into the lab, remind me to talk about sectionals. It'll make sense when I get there. It's funny. Nothing to do with chemistry at all. Okay, so these are the elementary steps over here. Or right here, elementary steps. So you have step 1 and step 2. So you can see, again, this is determined experimentally, and I'm not going to pretend to know how they figure this out, but you know, they figure out, scientists, chemists, they figure out, okay, when this reaction occurs, what happens first is NO2 molecules collide. So that happens first. Then it forms NO3, and then NO is formed. And then there's a second step where the NO3 from the first step now reacts with the CO. So this is what I mean, that a lot of reactions, the overall reaction isn't exactly how it works. So NO2 reacts with itself first, okay, producing NO3 and NO. Well, the NO is a product, so that's already formed, so that's just left alone. This NO3 is formed. That is what actually reacts with the carbon monoxide, not the NO2. Then that forms your other product, CO2. So what's an intermediate? Don't say it. Formed early, consumed later. When I say formed early, I mean formed in one of the first steps, and consumed later means it's used up in one of the later steps. And there's only 2 steps here. So what's formed in number 1 and then used up in number 2 so that it's not found in the overall equation? Pat Meehan. NO3, right. NO3, circle that. That would be our intermediate. Make sure you write that down somewhere so that you understand. It's formed in the first step, consumed in the second. Formed in the first, consumed in the second. Now, a lot of these elementary steps here, you can cancel things out so that your balanced equation makes sense. So what's one thing we can kind of cancel out here? What in the steps here, besides these 2, these are obviously, they're going to be canceled out. They're not going to be in here because one's on the product, one's on the reactant, so they cancel out. That's kind of how we relate it to the overall. Right, so these, one of those and one of those are canceled out because this only has one NO2 and one CO, there it is. One NO, there it is, and one CO2, there it is. So if you know the overall equation and you know the elementary steps, you can basically do what you need to do to cancel things out so that they match. The tricky part on an AP test or a quiz that I might give you, or a test, if I give you the steps and I ask what the overall is, you need to remember this. Okay, you need to remember, and there's going to be ways of figuring it out, but for sure, figuring out the intermediate, it's formed in the early step, and then it's going to be used up in the second or later steps. Okay. Questions? This is just one example. But these are called elementary steps. These are really what's happening when we're colliding, and then you can get your overall from that. So from now on, if I say reaction mechanisms, this is what it means. No questions. Okay. All right. The molecularity. Oh, by the way, 3 and 5 are the intermediates there. So good job, Maddie. So how would this one look different than this one over here? How many peaks would there be? How many intermediates were formed? Just one, so I would get rid of that, okay? So that would be your NO3, okay? So there would be your reactants, they would collide, okay? Actually, we could label these. You don't have to draw this, it's just, so what would be here? Look at your steps. What would be colliding here at the top? The 2 NO2s, right? So you'd have NO2 and NO2 here. This would be NO3. What's colliding up here? NO3 and CO, right? Okay, so just keep in mind that, you know, a lot of the stuff is related, so that is related to the steps. All right, so the next thing here, quick, is pretty simple, and then hopefully I can get into rate laws a little bit. Never have enough time. All right, so the molecularity of a reaction. Molecularity of a reaction. So that is the number of molecules reacting in an elementary step. The number of molecules reacting in an elementary step. So you have unimolecular, bimolecular, and termolecular, which is pretty rare, so we don't even need to get into that. Go ahead, take a break. I'm just going to put these up there, and then we'll finish up and then start the lab.